Hello. By the time I'm recording this, I'll have been a recent graduate from Western Governors University. I've got a Master of Science in Data Analytics. It was not an easy program, hence why it's a master's degree. And I guess my capstone actually won an award, so I figured it would be worth putting on my portfolio. My research question is, I ran a logistic regression model to see if phosphorus will exceed its maximum allowable threshold, 0.075 parts per million. That's not a lot. 1 part per million is 10 to the negative 6 grams. When a bunch of phosphorus goes into the river, see the red, from agricultural activities, waste, etc., it can create environments that end up with these massive fish kills. And fish is a very important part of the Idaho economy. I explain a lot in my notebook itself. I went crazy with the markdown syntax. But essentially, we've got your Python packages. You can see all the steps I use from data extraction to data cleaning. There were a lot of crazy fields. I was merging 2 data frames to make sure I got flow rates and all these predictors. There were formatting issues as well, converting timestamps. But I want to get down to basically my summary and my linear models. I ran some ridge and lasso regression to see if I could do any feature extraction, even things out comparatively. I did dummy variables on my site locations. This was not helpful to the logistic regression model, but it did provide some data insights. And this is a small screen, but it provided some data insights on which locations were under threshold and which were over, or at least positively correlated. So that did provide some much appreciated insights to my team. And here we finally get to multiple logistic regression. So I've got my predictors, only the quantitative variables. I've converted phosphorus to a Boolean value, true if it's over the threshold, false if it's under. And I did normalize the data set. I create a train test split with 70% training data, 30% testing data. Random state here to make sure I got the same results every time. Here I just show off how cross-validation works. It splits the data into 6 folds basically. And the first 5 it uses those as individual tests and provides different accuracy scores for each. The reason to use cross-validation as opposed to holdout testing is because it will reduce the chances of getting overfitting on this particular data set. Your model may be very good for the data set you're using, but is it good overall as a predictor? So you get 5 different results for those 5 splits. That's why you usually take the mean of your cross-validation. For this, I use 60-fold cross-validation, and my logistic regression accuracy was about 80%, so pretty good overall. Then using the holdout testing, I got a little higher, 81%. Typically, or in my experience on this data set, holdout testing was higher than cross-validation. Here I took a look at my coefficients, see if they provided any insight. I did notice that total solids and total nitrogen was an order of magnitude higher than any of the other predictors in this data set. So nitrogen and total solid, those were some of the strongest predictors. For logistic regression and most models, there's usually an intercept, throwback to calculus, that plus C. And my visualization for accuracy was an ROC curve. How these work is you have your true positive rate on the y-axis, your false positive rate on the x-axis, and this line down the middle represents 50%. That would be 50% false positive for 50% true positive. As long as your curve is above this, your accuracy is better than random. A perfect score would be straight up and straight across, a complete right angle. Additionally, I wanted another accuracy visual So I chose a confusion matrix. Predicted label, 0, false, or yeah, 1, true. And my true label, 0, false, 1, true. True being, yes, there is a phosphorus violation. So along the diagonal here are the true scores, right? It is false, and you predict it to be false. It is true, and you predict it to be true. And over here are the false negatives and the false positives. My false positives, so predicted as there is a phosphorus violation, but there isn't, were always higher than my false negatives. And at least for this business case, that's all right, because if you're predicting that there's phosphorus, or too much, and you tell the farmers to shut that down, that's better than not predicting the phosphorus at all and then having issues in the river. So I repeat this with different machine learning models. This was a master's program, so I had to show them something. I use random forest. You can see my results here. I'll get to those at the end. I use bagging, boosting. Boosting works by reiterating on top of the previous result and adjusting the model accordingly until you get the highest accuracy score available. That's kind of why you get these linear plots here. It like adjusted to here, then it adjusted to here. Finally, I used XGBoost. I know this is a little older, but it's been used to win some Kaggle competitions. With XGBoost, there's different hyperparameters and different availabilities that you can use to adapt your model to give it the benefits of boosting, but also the necessary model adjustments needed to get a more accurate data set. It's been a while since I've looked at this, so apologies. I'm rusty on the model mechanics right now. Get my cross-validation, my test data score. Again, holdout testing, always higher than cross-validation. And you see, even though this is boosting, I'm not getting that straight line type of curve. That is one of the benefits to XGBoost. It has additional parameters that can help increase your accuracy. I repeat this with a lower variable model. The reason I did that is by the time you're measuring phosphorus, you're measuring all the other chemicals that are in the water system. So these 4 variables here are the only true predictors of phosphorus before it gets measured by our specific chemical instrumentation. Logistic regression is used here. It's only 4 variables. Again, total solids very high. Showing the curves again, the confusion matrix. More false positives, so looking good there. Again, random forest, bagging, boosting. See that linearity, which is a trait of the boosting model. And then XGBoost without the ions. Again, now you get this more natural curve using the XGBoost model. For multiple logistic regression, these were the end results that I came away with. My pseudo R squared using that stats model was about 36%. On the lean model, so no chemical ions, just those predictors here, you got about 20%. Accuracies were they were the exact same. Even if you got rid of all those chemical ion fields in the data set, you were still walking away with a similar accuracy for this particular data set. But since your R squared actually shifts, that kind of gives credence to my thoughts that there could be overfitting in this data. Here I mentioned some of my limitations. The data quality, I had a small record count. For machine learning or any type of model, the more data you can include, the better. There was going to be bias in the data. The canals get shut off during the winter season, so I can't get a full representation. And the phosphorus contributions are seasonal as well. There is a farming season. I mentioned here how only 4 of those variables can be used as predictors. And I mentioned the limitations of logistic regression. So logistic regression, it's going to assume linearity with respect to the logit. Look up multiple logistic regression if you want to see that equation. And the nonlinear models, in this case, did have higher accuracy scores, but not by much. I have some proposed actions. You can improve the model by sticking to the statistically significant variables. You can use ensemble modeling and kind of mix multiple models. After enough data is collected, which will happen over time, you can even try a deep learning model, a neural network. As for what we have now, we could just flag the anomalies as our prediction accuracy increases. If our accuracy right now is 75% and we're getting false positives or false negatives, we should take a look at them. I also mentioned linear regression. I suspected it might give higher accuracy scores since it allows the phosphorus levels to vary as opposed to just be binary, like above threshold or below threshold. And I also proposed a new calculation that would just give you a mass rate detection limit so that you could calculate the phosphorus levels in the river as a rate instead of having to do any modeling whatsoever. As I mentioned previously, Idaho, big fishing industry, and hopefully this was able to contribute to the research where I work. So that's what I was working on these past couple months, and thanks for listening to me.